from Shenzhen University. I will now describe our work, PDFactor, learning track perspective, view policy diffusion field for multitask robotic manipulation. Okay, now let's begin. Robotic manipulation is a common task in involved AI, requiring robots to interact physically with objects to complete goal-directed tasks. Recent advances focus on using vision and language inputs to make this system more general and intuitive. However, learning effective policy from such high-dimensional inputs demand changes, especially in terms of data efficiency and control accuracy. This sets the stage for different policy learning. Okay, let's look at two common approaches in robotic manipulation with vision and language inputs. The first is end-to-end vision language action learning. This method maps raw observation directly to robot actions, and they have shown impressive scalability because the entire process is learned jointly, and they are conceptually simple and adaptable across tasks. However, this simplicity comes at a cost. They typically require massive amounts of human demonstration or interaction data to perform well, which can be expensive to collect. Second category include keyframe-based method. This method breaks down the problem by first predicting the next keyframe, typically the desired 6th degree of freedom and the effective pose, and then use a low-level motion pattern to execute the movement. This design makes policy learning more efficient and often simplifies the overall learning process. Our method follows a keyframe-based paradigm with a focus on efficient and accurate pose prediction. Okay, we see keyframe-based policy learning. There are two common practices in the action map. The agent learns to predict an actual map, essentially a feedback over the 3D workspace that indicates the probability of passing the end effector at each location. The point with the highest value corresponding to the most promising next pose for execution. This method has a couple of notable strengths. First, the action space is spatial aligned with the perception space, making the policy easier to learn. Second, the network only needs to predict a heat map-like output, which is a relatively simple learning target. This allows for lightweight network architecture and faster inference. But despite these advantages, this approach has its downside. To represent the ineffectable distribution, the action space is usually discretized and modeled as a categorical distribution. Unfortunately, the number of beams needed to achieve fine precision increases exponentially with the action space dimensions. This quickly becomes computationally expensive and make it hard to accurately predict high-resolution actions. Now, let's move on to the second category, implicit policies, which mainly include image-based and diffusion-based methods. In this presentation, I will focus on diffusion-based approaches, which have recently become very popular in robotic manipulation. These methods are powerful because they can represent any continuous on the distribution, and more importantly, they can naturally model multi-module action distributions. Conceptually, a diffusion-based policy learns a gradient field over the action space. During inference, actions are generated by interactively causing noise, effectively performing a kind of gradient descent in the known action space. To accurately capture the action gradient field, the neural network used for score estimation are typically large, which makes the inference process slow and computationally expensive due to the many interactive noise steps. Additionally, since the learned action gradient field is not explicitly aligned with the perception space, the learning process can be less efficient and the convergence more slowly than action gradient. So, in this work, we propose a novel hybrid action implementation, which we call policy diffusion field. Our goal is to combine the strengths of both action value map and implicit poses, achieving the spatial alignment and the efficiency of action value map, while maintaining the flexibility and the expressiveness of diffusion-based approaches. Specifically, we aim to model the distribution of the next keyframe and the effective pose, conditioned on both language instructions and RGB visual observations. Here how it works. We start by constructing a 3D point cloud of sets from the multi-view RGB input. Then we use an MLP to encode the point into a set of point-wise feature. To effectively represent the spatial structure, we project these features onto 3 orthogonal planes. Top down, from back and sideways, using max pooling. This gives us a compact yet expressive tri-perspective representation of the sets. Once we obtain the tri-perspective feature plans, we broadcast them into a dense cubic feature volume. This volume is spatial aligned with the perception space, meaning each 3D location in the set corresponding to a lantern feature vector that describes the 6th degree of freedom distribution at that point. To decode action gradients from this field, we adopt a lightweight noisy analogy. We start by sampling a noise 6th degree of freedom action from a standard Gaussian distribution. The noise action corresponding to a specific location in the sense. We then interpolate and aggregate the tree pair features at that location to construct a lantern vector, which serves as a compact representation of the sets at that specific pose. The denoising MLP packages noise action as input and uses the time state of the diffusion process and the lantern vector as conditioning. It outputs an action gradient, which is used to denoise the current action sample. By iteratively refining the action. Through this process, we gradually move from noise to a clean, meaningful action that is consistent with the sense geometry and the task structure. Well, our proposed method brings several key advantages thanks to its hybrid representation. First, because the policy diffusion field is directly aligned with the perception space, each point in the 3D sense corresponding to a meaningful lantern feature. This spatial alignment significantly simplifies the mapping from observation to action, making the learning process more efficient and stable, and leading to a faster convergence. Second, unlike conventional diffusion-based policy that rely on neural networks, we use a lightweight MLP as the noisy decoder. This design makes our inference process an order of magnitude faster than previous diffusion-based methods, while still maintaining competitive performance. Third, our method inherits the benefits of implicit poses. That is, we can model continuous action distribution without discretization. This allows us to generate arbitrary precision actions and ensure strong scalability to more complex tasks. To demonstrate these advantages, we evaluate our method in both simulation and real-world setting. In simulation, we test on 18 diverse tasks from the IO bench benchmark. In the real world, we validate our approach on 6 manipulation tasks using a UR5 robot. Here, we present the results of our method. As we can see, our method outperforms all baseline, including both action value map and the diffusion-based method, with consistent improvements across most tasks. The second figure was success rate against the training set. Our method achieved faster convergence to the spatial alignment and efficiency of the policy diffusion field. Thirdly, involves the inference speed. Compared to previous diffusion-based method, like the 3D diffuser actor, our approach is one order of magnitude faster, primarily due to the use of a lightweight noisy MLP and the hybrid representation design. Finally, the fourth figure shows the result of real-world experiments across 6 tasks. Our method achieved we proposed the PDFactor, a new approach of robotic manipulation that introduces a hybrid action representation by grounding continuous and multimodal action directly in 3D perception space. Our method simplifies policy learning and improving spatial listening. And the tone of our framework is the policy review, which enables us to learn accurate and scalable 6-degree of freedom and purpose distribution using a lightweight and efficient deployment network. Together, this design choice allows PDFactor to achieve state-of-the-art performance in both simulation and real-world tasks with strong generalization and fast inference. Okay, thanks for your attention.
Thanks for the presentations. And I noticed that you use a small NLPs to maintain a fast inference, and why use a simple NLP is enough for denoising the action space?
Yeah, you mean why we use all NLP as an encoder? Yeah. Well, I think the reason a small NLP can work is that it does not need to learn the entire scalar function of the diffusion field from scratch. Instead, it only needs to decode the local action score at a specific point using already learned lesson feature. And you can see this slide. PDFactor uses a tree-edge transformer to construct a spatial aligned representation of the action field. And this means the burden of learning complex spatial relationship is handled by the transformer. And the NLP, just performing lightweight decoding, conditioned on the aligned representation. Yeah, I think.
Okay, thanks.
That's a quick question. That's all. My question was where do you get the features from, and how big are the channels?
You mean how I get the treatment features from the point cloud?
How do you get the features from the point cloud?
How to get the features from the point cloud?
Well, like each point has a feature, and where does the feature come from?
Yeah. Let me see. We just when we constructing a 3D point cloud from the RGBD image, then we use an NLP to encode the point cloud into point-wise feature. Then we